In this video, I'm going to talk about general problem-solving strategies. So these are problem-solving strategies that you could use with your students or in our class. And the first one includes guess and check, or trial and error, which is also involved in teaching kids estimation and checking. Next one is looking for a pattern, creating a table to organize your thoughts, drawing a picture. With kids, you can also make, well, with grown-ups too, make a model, not just a picture. You can work backwards, and you can create a smaller, simpler problem to try first. So I'm going to show you several of these strategies in this video. And finally, you can describe and solve the problem algebraically, but that's not generally one that I would use in your first, second, or third grade class. Notice that these are general problem-solving strategies, not specific to a particular problem. They work on lots of kinds of problems. So let's look for a second at algebra, because I know you guys can do algebra. What would be a good general problem-solving strategy? Add 3 to both sides? Use algebra? Guess and check? Or divide by 2? What do you think? Or work backwards? Okay, let's cross this one out because it's too specific. It's not a general strategy. What else should we cross out that's too specific, not general? That one. Right? So we can use algebra, we can guess and check to find the answer. So you can guess, I guess the answer would be 2. Let me see if it works. 2 times 2 is 4, plus 3, that's 7, that's too low. So let me guess 3. 2 times 3 is 6, plus 3 is 9, too low. How about 4? 4 works. So you can see, that's guess and check, right? Guess and check is fine there. And you can also work backwards, which we'll talk about in a minute. So let's look at this problem right here and see which problem-solving strategy would work best for this problem. We're looking at what the ones digit of 2 to the 4,000 would be. That is, what number would this end with? 2 raised to the 4,000th power. I'm just going to pause the PowerPoint for a second because I know if you're like me, you want to reach for your calculator and go 2. Let me use my X to the Y key, my power key, and raise it to the 4,000 power. It should work. Let's see. Whoa, what is that? So what that is, it's not an error. That E is not an error message. It's saying that it's just a really giant big number times 10 to the 1,204th power. Wow! And there's no way that that 6 there is the ending digit. It keeps going on and on and on, long past that. What it's saying is take this long decimal and move the decimal place over 1,204 times. Wow! And we'll get our number. Well, so the calculator didn't really work, right? So I guess we're kind of stuck trying a different problem-solving strategy than using the calculator, right? So we're going to look for a pattern, and we're going to use a smaller problem. Now, these I know you can get on your calculator, and I want you to actually pause the video. Seriously, whoops. Don't look at that last slide I just accidentally clicked on. Actually pause the video right here and try to get these and see if you see a pattern. It's much better if you try it than if you just go on to the next slide. Really, pause the video. You know you have a minute. Pause, work out the powers. Now I know you paused that video, right? Now let's look at the digits that we end up with. We have 2, 4, 8, 6 for our ending digits. And again, 2, 4, 8, 6 for our ending digits, the ones place. So the question is, where would 2 to the 400 go in this table? That might help us figure out where 2 to the 4,000 would go, right? And how do you know? So 2 to the 400 would go in this 4th spot on the table because all the powers that are divisible by 4 will end up in that 4th spot. So 2 to the 400 would end in a 6, because all the ones in this 4th spot end in a 6. So what we're noticing is that the pattern of the digits has a pattern of 4s, right? It repeats itself every 4. And since 2 to the 400, since 400 is divisible by 4, we're going to end up there. What about 2 to the 403? And then we'll talk about 2 to the 4000. 2 to the 403 would end in an 8. Why? Because you would end up here. Whoops, go back, sorry. You would end up here because 2 to the 400 would be here. Then here's 401, 402, 403. In other words, when you divide 403 by 4, the remainder is 3. So it would end up in this row. But there are a lot of ways to think about this. So where would 2 to the 4000 be? You guessed it, right here, right? So 2 to the 4000 would also end in a 6. Now, for some people, that was a little fast, right? So I want to try a different example, different pattern. And you should also read the textbook and try some more examples. Now, look at this one. This doesn't have any numbers in it. This is awesome. Plus, it has cats in it, which is also awesome. So how can I find the next letter? So if the pattern is C-A-T, 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 you know what the next letter is, right? It's a C. So what's the pattern going by? Every how many letters till I get to a C again? And what would the 99th letter be? Think about this for a second. It's the pattern. C-A-T. T is the 3rd letter. And then again, C-A-T. T is the 6th letter. And then again, C-A-T. T is the 9th letter. The 9th letter is a T. So where would the 99th letter be? And where would the 100th letter be? What would it be? So all of these guys, the 3rd letter, the 6th letter, the 9th letter, they're all divisible by 3. So think about the 99th letter. That's also divisible by 3. And so it will be a T. Now how about the 100th letter? Go one more. After T, we go back to C again. So the 100th letter is a C. Now I hope that helped. But I really, really, really want you to think about this more, not just in this quick video, and do some more. So you've got some of these on the project to talk about with each other and to practice more. Now let's look at another kind of problem-solving pattern. A man goes to the track each week to bet on horses. That's not a good habit at all. The first week, he triples his money. What's that mean? Means he multiplies his money by 3. And then he loses $12. He saves what he has to play the next week. What's he doing? He should quit. Never bet on things. The next week, he takes his money back, doubles it, and then loses $40. See, I told you, don't bet on things. Then the next week, he tries again and quadruples his money. What the heck is quadruples? Means times 4. He decides it's a great time to quit betting, oh yay, and keeps the $224 he has won. How much did he start with? Wow, how could you even do this problem? It looks kind of like algebra, right? We go back. So like, we could say a man goes to the track each week to bet on horses, and that's X. But believe me just for a second, algebra is super hard on this one. So I'm going to show you something else for now, and then we'll look at the algebra. So here's working backwards. So we're going to go backwards. We're going to say, okay, he has $224 that he kept, right? Right before that, what happened? He had quadrupled his money. So if we divide by 4, that's the opposite of quadrupling. Quadrupling is multiplying by 4. Let's divide by 4. He had $56 because 56, and then he quadrupled it, right? 56 times 4 gets me $224. All right. Let's go backwards one more step. See right here where it says he lost $40? So what did he have before he lost the $40? He had 96 bucks. Because 96 minus the 40 gives us 56. Do you see what we're doing? We're not just going backwards, we're doing the opposite at every step. So 96 divided by 2, right? It said he doubled his money. So instead of doubling times 2, we cut in half. So we're at 48. So now we're here at 48, and it says he lost 12. What's the opposite of minus 12? I'm going to add 12. So 48 plus 12 is 60. And now here it says tripled. He tripled his money. That means times 3. What's the opposite of times 3? Divided by 3. He started with $20. Ta-dum! And actually, I know you're not used to working backwards, but boy, is that easier than the algebra. Let's look at the algebra. So he starts with X amount of money. He triples his money and then loses $12. That's 3x minus 12. Then he doubles that and loses 40. That's a little hard to read. It's 2 times the 3x minus 12 minus the 40. Wow. And then it says he quadrupled that. That means 4 times all of this. That's that. Ooh, it's getting messy. And all of that is equal to 224. And that's just tough. But I will say that if you tried to solve this, what you would do is divide both sides by 4 to get the 4 off. And then you would divide both sides by 2 to get the 2 off. You would basically be solving as the same as working backwards. So solving an algebraic equation is just like working backwards. Therefore, working backwards with your kids is preparing them for doing algebra. Really important stuff. Now, one last one. What problem-solving strategy would work best on this problem? Augustus de Morgan was a mathematician, this is true, he really was, who lived in the 19th century. That means the 1800s. I know that's stupid. He said, I was X years old in the year X squared. When was he born? So, again, it looks like algebra, right? Because it's got X's in it. But I'm going to say you can't use algebra. You really can't. Why can't you use algebra? Because there's nothing to put this equal to. So, I was X years old in the year X squared. Trial and error is your way to go. So, what I mean by trial and error is try 10. So he was 10 years old, you square it, in the year 100. Does that seem reasonable? No, because he lived in the 1800s. So what would you try next? Would you try a much, much larger number? I would, because 100 is kind of low. So 30, he was 30 years old in the year 900, right? You square the 30, is still kind of low. So pause the video right now. You don't want to. You just want to watch the rest of the video. I'm telling you, it'll be so much more fun if you pause it and see if you can find the answer without me. I'm going to wait here. You pause the video, see if you can find it. You really did pause the video, right? Didn't he live in the 1800s? We want to get closer to the 1800s. If you didn't pause the video yet, pause it now. And you should find that he was 43 in 1849. It's the only one that works. 44 gets you too high. So 43 is perfect. Uh-oh. Oh, I hate when this happens. We didn't answer the question yet. When was he born? So, take 43 away from 1849. He was born in 1806. Yeah, why? Because he was 43 years old in 1849. So he was born in 1806. Wow.